Hi, everybody, and welcome back to AP Physics 2. Today, we'll be looking at radioactive decay and doing a little bit of mass energy equivalence. As always, we'll start just by running through the agenda. First, there's going to be a lesson overview. We'll talk about everything that we're going to do today. Then we'll go through our daily warm-up. We'll start off with the question we left with yesterday and do a little warm-up, get your brains moving. Then we'll talk about what you need to know, all the key points that you need to be really good at radioactive decay. Then we'll do some guided practice questions from the AP Physics question bank. And once we're done with those, we'll do a debrief and summary. We'll talk about what we talked about and made sure that you learned what you meant to learn. Finally, we'll do an AP exam practice question, and that's the question that we'll use to start class tomorrow. So, I'm Joe Mancino from Glastonbury High School in Glastonbury, Connecticut.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas. Let's go ahead and take a quick overview of our lesson today. First off, we'll begin discussing nuclear reactions and how unstable isotopes lean towards nuclear reactions and half-life.
Then we'll talk about different types of radioactivity. We'll talk about alpha, beta, and gamma particles. We'll talk about a small energy unit called electron volts.
Then we'll get to mass energy equivalence, which is basically equals mc squared, but we'll also discuss mass defect and binding energy.
And here's what we think that you know coming into today's lesson. I think you know what an atom looks like. You have a really good sense of the structure of an atom. I think you know that objects spontaneously fall to lower energy. If you drop something, it falls to lower gravitational potential energy. If you stretch a spring and let it go, it snaps back to lower spring energy.
And by the end of the lesson today, we hope that you can distinguish between three different types of radioactive particles. You can balance a nuclear reaction. You can calculate the difference in mass when a nucleus reacts, and calculate how much energy is released when a nucleus reacts.
We'll be working on making claims and predictions about natural phenomena, and we'll be connecting concepts across topics. We will do a little bit of math, but we're not going to stress the math. So here it is, the warm-up question from yesterday. Now, there is a bit of a tricky piece in there with part B, so we'll see how you did. First off, let's just review. I hope you took a screenshot yesterday. We had this hypothetical atom with 4 marked energy levels and then a marked ionization energy. Your job was to figure out what happens if electrons in the n equals 3 level, that's that negative 0.75 electron volt level, what if they emit photons? What kind of transitions were possible? Well, certainly there is a transition from n equals 3 to n equals 2, but there's also a transition from n equals 3 to n equals 1. Of course, if an electron transfers from n equals 3 to n equals 2, well, then it could also afterwards transition from n equals 2 to n equals 1. So there were 3 possible transitions that electrons could have undergone if they emitted photons after having been at energy level 3. Of those transitions, could you calculate which one had the longest wavelength? Now, I'm hoping that you were able to just figure out which one had the longest wavelength. That would have been great. If you identify the transition from level 3 to level 2 as having the longest wavelength because it has the least amount of energy, that's awesome. We suggested in the last presentation how you could have done this, but it was really tucked in there. Energy is Planck's constant times frequency. Frequency is speed over wavelength. So you could have said, well, wavelength is Planck's constant times the speed of light divided by the energy. And if you do that, if you take Planck's constant and multiply by the speed of light and divide by the energy, you get about 551 nanometers. I wasn't really expecting you to numerically get that unless you happen to have a copy of the AP Physics equation sheet, which does make this a little easier. Planck's constant times the speed of light is conveniently 1,240 electron volt nanometers. So if you took that divided by the 2.25 electron volt photon, is 551 nanometers. But the ionization energy is just the energy difference between the ground state and the 0 electron volt state, and that's 12 EVs. So if the ionization energy is 12 EVs, what would happen if this atom absorbed an 11 electron volt photon? Well, nothing. There is no jump with a difference in energy of 11 electron volts. However, if it absorbed 14 electron volts in a single photon, that is enough to ionize this atom, to promote an electron from the lowest energy level past the ionization energy.
Okay, and here's your warm-up for today to get your brains thinking about nuclei again. So a radioactive nucleus is at rest and it undergoes a fission reaction, releasing energy. Which of the following correctly categorizes the products of the reaction? So looking at the 4 answers, I noticed that every single one starts with the sum of the masses. So take that down really quick. Sum of the masses is greater than the original, sum of the masses less than the original, sum of the products is equal, and sum of the masses of the products is equal. That's A, B, C, D. That's your 4 answer choices broken down into pieces. And there's no way that you probably know this yet, but that's okay. Scientists knew that this was going on before we totally understood it too. The answer to this question is actually B. The sum of the masses of the products is less than the mass of the original nucleus because some of the mass of the original nucleus was converted to energy. And now we'll move on to what you need to know. All right, so what you need to know from today's lesson, nuclear reactions. The strong force is what holds the nucleus together. We talked about that in the last lesson. Radioactive decay is spontaneous and governed by statistics. Determine the material's half-life and predict the results of the time passing. 3 types of particles that are released when the nucleus decays. Total atomic number and total mass number are conserved in a nuclear reaction. And when we talk about mass energy equivalence, we need to know that AMU and EV describe very, very small measurements. Fission and fusion reactions result in less mass per nucleon. The mass defect, we'll talk about that later, is related to the energy given off in these reactions. And of course, the famous E equals mc squared, which everybody thinks you learn in physics whenever you take physics. But we'll talk about how E equals mc squared fits into all of these ideas.
So good news, we're in physics, and today is the day that we get to do it, E equals mc squared. But before we get there, we got to start at the beginning. We're going to talk about what nuclear reactions are and how they're different from the chemical reactions that you learned about in chemistry class. A nuclear reaction, you finally get to do what your chemistry teacher said don't do. We get to poke the nucleus. So I just want to review how many protons, electrons, and neutrons are there in uranium-238. Yesterday, we talked about the way that we label the chemical symbol for an atom, what that 238, what that 92, even what the letter really mean. That 92 means that there are 92 protons. If it's an electrically neutral atom, there are also 92 electrons. But then there's that 238 number. That's the total number of nucleons. So 238 nucleons, 92 of them are protons, and the other 146 are neutrons.
Well, for various reasons, certain isotopes are not stable. And remember, isotopes are the same atomic number, but different mass number. These are called radioactive isotopes. And radioactivity really is just the spontaneous breakdown of unstable nuclei. And when they break down, they emit particles and rays.
Atomic nuclei are held together by the aptly named strong force.
And without the right arrangement of neutrons and protons, the geometry of the nucleus can't support itself, aka it becomes unstable. And pieces of that nucleus can break off, eventually changing the material itself, changing the element itself.
So the rate at which that happens is governed by statistics, and a big enough sample of radioactive material all breaking down at the same time, we look at the amount of time it takes for half of a radioactive sample to undergo radioactive decay, that spontaneous changing of a nucleus by emitting particles and rays. Half-life is the time it takes for half of the sample to become something else. For example, radium-226 has a half-life of 1,620 years. That's a while. After 1,620 years, if you started with 100 pounds of radium, you would end up with 50 pounds of radium and 50 pounds of other stuff. After another 1,620 years, there would only be 25 pounds of radium and 75 pounds of other stuff. That is the idea of half-life. So take a look at this graph. The number of undecayed atoms after a certain number of hours have gone by. Your challenge is to identify what the half-life is. What is the half-life of this sample? How much time does it take for half of the sample to decay? Well, I think you might notice that the sample starts off pretty high up on the y-axis, and after one half-life, there's only half as much. The half-life was 3 hours. And you'll notice that every 3 hours, there's half as much material as there was before. The rest of it, that initial total mass, it's all still there, but it's just not that stuff anymore. It's the byproducts of that stuff. So in this question, we see a radioactive sample. It decays at 4,000 counts per minute, 4,000 radioactive events per minute. 12 minutes later, the decay rate is 1,000 counts per minute, 1/4 as much. What would be the predicted decay rate after 18 minutes have gone by? Well, we need to figure some stuff out. We need to figure out how many half-lives went by in that initial chunk of time. So, can you figure that out? How many half-lives went by in the first 12 minutes? We went from 4,000 counts a minute initially to only 1,000 counts a minute after 12 minutes. Well, that's 1/4 as much. So 1/4 as much means 2 half-lives went by. If 2 half-lives went by in 12 minutes, that means the half-life is 6 minutes. If 18 minutes have gone by, that's 3 half-lives. So 4,000 counts a minute becomes 2,000 counts a minute. That's 1 half-life. 2,000 events per minute becomes 1,000 events per minute, a second half-life. The third half-life decays from 1,000 counts a minute to only 500 counts a minute.
All right, so this is polonium-216, which actually doesn't have any significance in this problem, but we know that its half-life is 1/7 of a second. The question is, what percentage of a polonium-216 sample will decay in 1 second? So in 1 second, how many half-lives have gone by if we know a half-life is 1/7 of a second? That tells me that I have 7 sevenths, which means there's 7 half-lives. So over 7 half-lives, we know that half of the material has decayed every time. So that turns into 1/2 times itself 7 times. So 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2 gives you 0.78%, which is left of the original substance. And if you take 100% and subtract 0.78, that tells you 99.22% has decayed. Which brings us to the different types of radioactivity. These are the 3 main particles that we are talking about today: alpha particles, beta particles, and gamma particles. Now, alpha particles, we know the symbol alpha is kind of like that fish-looking thing, but that's the Greek letter alpha. Alpha particles are basically just helium nuclei, and each of those consists of 2 protons and 2 neutrons. Alpha particles have a positive charge +2 because they have 2 protons. And alpha particles are only slightly affected by a magnetic field because they have a large mass, relatively speaking, to the other types of particles we're talking about today. And since they are so large, they're actually easily stopped by a sheet of paper or even just tissue paper.
Beta particles, you've actually heard of them before. The symbol for a beta particle, well, it's the Greek letter beta. Betas are electrons, so they have a negative charge. Sometimes they're called beta minus. They're just electrons. They follow everything that you know about electrons. Beta particles can be greatly deflected by a magnetic field because of their small mass, and they are charged particles, so they follow all the rules that you learned about when you learned about magnetic force. Beta particles penetrate matter more than alpha particles, but they're not very penetrating. Beta particles can be stopped by metal foil or several sheets of paper. Gamma rays are different. The symbol for a gamma ray is the Greek letter gamma. Gammas, they're just high energy light. They have a very short wavelength, high energy photons. Gamma rays have no charge. They're light waves, those aren't charged. They're not deflected by a magnetic field. Again, they have no charge. But gamma rays are the most penetrating form of radiation. Stopping a gamma ray requires a lot of heavy material, like a lot of lead or a lot of concrete. Okay, so here's a riddle if you're trying to avoid radioactivity. You have 3 radioactive samples. One of them emits alpha particles, one emits beta particles, and one emits gamma particles. And your challenge is you have to hold one, put one in your jacket pocket, and eat the other. So what do you do? Now, this situation is never going to happen. Don't eat radioactive samples. Don't try this at home. But like, what do you do? Okay, so good news. You can hold the alpha particle. Your skin is enough to stop alpha radiation. If you have a sample emitting alpha particles, your skin will stop the particles from entering your body. Good news, your jacket pocket is enough to stop those beta particles getting into your body and causing any trouble. And well, nothing but a few feet of lead is going to stop those gamma particles anyway. So actually eating it is no more deadly than any of the other options. Also, don't eat radioactive samples that emit gamma radiation. It's like a good rule. So here are the particles that you need to know about: neutrons, protons, and electrons, along with their charge number and their mass number. And here are alpha, beta, and gamma particles with their charge number and mass number. Definitely notice that an electron has a charge of -1 and a mass of 0, or it has no nucleons. A beta particle is an electron. I even gave it the symbol electron. Gamma particles are photons. They don't have mass, they don't have charge, they're just energy.
All right, so in nuclear reactions, nuclei break apart to create new materials. We kind of touched on that earlier. But once they've broken apart to create new materials, the atomic numbers must balance. The total charge of the reactants equals the total charge of the products as well. The mass numbers must balance, and the number of nucleons before a nuclear reaction is the same as the nucleons after a nuclear reaction. All of these criteria have to be met in nuclear reactions. So let's see our first type of nuclear reaction, which is an alpha decay.
Oh, there it is. In alpha decay, an unstable nucleus produces what's called a daughter nucleus, and it releases an alpha particle. So this is alpha decay. Notice the total nucleon number adds up, the mass adds up. There are 238 nucleons before the reaction and a total of 238 nucleons after the reaction. The total charge adds up. There are a charge of positive 92 before the reaction and a charge of positive 92 after the reaction. Let's take a look at beta decay. Mr. Eden?
All right, our second reaction is beta decay. And this is when a neutron becomes a proton and ejects a beta particle, which again was just an electron. And notice that your total mass number still adds up. 234 is equal to 234 plus 0. Now the atomic number gets a little bit tricky. You've got 90 is equal to 91 plus -1 from the electron. And the reason that the 90 goes up to a 91 is because one of those neutrons became a proton and changed the atomic number of that element. So we actually have an entirely different element after this reaction has undergone.
And finally, gamma radiation. Lots of nuclear reactions produce gamma radiation. In this case, it's actually that first reaction from alpha decay. Alpha decay does that frequently. It releases a gamma ray. That's that purple wiggle right there. It doesn't have any mass. It doesn't have any charge. It simply carries away energy.
All right, here is a question for you. If you have oxygen and it undergoes some type of reaction that gives off an electron, what type of reaction is this? How would you complete that? The way you would complete this is, I know what fits inside the blank, the mass number can't change because the mass of the electron is 0, but the atomic number is going to go up by 1. So the new atomic number is 9 instead of 8. So instead of oxygen, we have fluorine.
So you're saying the material became something else. It transmuted, it's different now?
Totally different because it has a different number of protons, which gives that element its identity.
Wow. Okay, so let's see if we can sort this one out. A deuterium nucleus interacts with a lithium nucleus. I'm going to show you a few different sets of products, and your job is to identify which one could not come from this reaction. So I want you to focus on this, sort of the bottom right part of your screen. When deuterium combines with lithium, the products, pay attention to the charge number and the mass number. Here they are. Which of those doesn't work? A total charge of 4 and a mass number of 9. Well, let's take a look at the first one. In the first one, I see a total charge of 2 plus 1 plus 1. That's 4. And a total mass of 4 plus 3 plus 2. That's 9. In the second reaction, I see a total charge of 2 plus 1. Ooh, that is not 4. So the second one violates the rules both in charge number and mass number. You can double check me on the rest of them. Grab a screenshot. I think I'm right.
All right, so let's move on to mass energy equivalence. So to start off with mass energy equivalence, we need to know that in order to analyze small things, we need really small units. And these special units only work on the scale of atomic interactions. And the first one that we've actually discussed before is atomic mass unit. And it's frequently used to measure the mass of an atom. And 1 AMU is defined as 1/12 the mass of a carbon-12 nucleus. It's about the mass of a proton or a neutron, although protons have a slightly different mass than the neutrons.
The electron volt is a small energy unit. It's equal to the amount of energy gained when one electron is accelerated through a 1 volt difference. You probably remember energy is Q times V. Well, if you're using coulombs, then you're talking about bigger energy units. But if your unit of charge is an electron, you've got the electron volt as your energy unit. It is a unit of energy. It is not a unit of voltage. It's a charge times a voltage. That's an energy. So energy is charge times voltage. 1 eV is equal to 1.6 times 10 to the negative 19 joules. They're quite small.
And since they are so incredibly small, we typically use the unit mega electron volts when dealing with macroscopic events. And 1 mega electron volt is equal to 10 to the 6 power electron volts, 1 million volt electron volts, which is equal to 1.6 times 10 to the negative 13th joules.
So Einstein discovered why it is that nuclear reactions release tremendous amounts of energy and described it with one simple equation. E squared equals P squared C squared plus M squared C to the fourth, where P is momentum, E is energy, C is the speed of light, and M is mass. Of course, that doesn't have much of a ring to it, but when stuff's not moving, when its momentum is zero, when P equals 0, it says E squared equals M squared C to the fourth, or simplify it out, E equals MC squared.
And why is it important that momentum is equal to 0? It just means that we're talking about the mass at rest. It's not moving. And according to classical physics, it would have no energy. But Einstein disagreed. He said that whether or not the mass was moving, it still had energy. So if it was at rest, this energy is called the rest energy.
So E equals MC squared, where E is the rest energy, M is mass, and C is the speed of light. I'd say take a screenshot, but I feel like you knew this one when you signed up for physics. Anyhow, a useful conversion you would have gotten had you had this stuff on the AP test is that one atomic mass unit, 1 U, has the energy equivalence of 931 MeVs per C squared. MeVs per C squared seems like a really weird mass unit. I promise you, MeVs per C squared is a mass unit. Here's why. Here's why it works. If E is MC squared and 1 U is the mass, if 1 U equals 931 MeVs per C squared, and we multiply that by C squared, we get an energy of 931 MeVs. That means that 1 U of mass, about 1 proton's worth of mass, has an energy equivalent of 931 million electron volts.
So the mass of 1 AMU is 1/12 of the mass of a carbon-12 atom, which is 1.66 times 10 to the negative 27th kilograms. But we just said that it's also 931 mega electron volts per C squared, and it's 931 mega electron volts of energy.
So you're saying that mass in kilograms can be converted to mass in a unit of MeVs per C squared, and
exactly
can be
what we're
MeVs of
saying.
energy?
That's exactly what we're saying. So it really just leads to ridiculous conversions, but they come out to be pretty useful later on. If the mass can be converted into energy, then we can calculate the energy available from any piece of mass.
Any piece of mass? Because I can think of a piece of mass with very little energy. True story. My college roommate, my second semester, he slept for an entire semester. He was a dent in the bed above me. He had a mass of 66 kilograms. What was his rest energy in joules? Notice I've given you the mass in kilograms, and I'm asking for the rest energy in joules. He had macroscopic mass. So we use E equals MC squared, and we take his mass and multiply it by the speed of light. Remember to square it. If E is MC squared, then my roommate was worth 3.7 times 10 to the 31 MeVs, or about 6 million trillion joules. There it is. That's a lot of joules. That's 6 billion joules. which happens to be, because I was wondering, this is what you do when you're a physics major and you have this guy for a roommate, that's 1.65 times 10 to the 12 kilowatt hours, which would cost about $3 trillion if his mass could have been converted into electricity. Don't convert your college roommate's mass into electricity, and also don't swallow radioactive samples.
So I hear pretty frequently, what is the meaning of E equals mc squared? So what does that equation actually mean? A lot of people think it means that matter and energy are the exact same thing. They aren't necessarily the same thing. But mass can be converted into energy, and energy can be converted back into mass. It sounds tame, but it's pretty revolutionary. And you'll see why in just a second.
The effects aren't really noticeable in everyday life. You never notice that your car is slightly heavier when it has more kinetic energy. We don't pay a lot of attention to E equals mc squared in our regular day-to-day macroscopic life because the energy usually can't be used.
And we can't easily turn coffee grounds into energy like, great Scott, Dr. Brown. But difficult doesn't mean totally impossible.
When Einstein published his theory in 1905, the response of the physics community was disinterest. They thought this E equals mc squared thing was interesting, but would ultimately achieve nothing.
And even Einstein was of this opinion, saying there is not the slightest indication that nuclear energy will ever be obtainable. It would mean that the atom would have to be shattered at will.
Well, now we do that. One of the ways that we now tap into that energy mass equivalence is during nuclear reactions. In fission reactions, mass is converted into energy when nuclei divide. In fusion reactions, nuclei are forced together to form a larger nucleus. So in a fission reaction, nuclei break apart. In a fusion reaction, nuclei come together.
All right, let's see how we can use this in terms of rest mass energy of a proton. So we're given that the proton's mass is 1.007276 U's. And if we use E equals mc squared, I know I can plug that mass directly in, but that new number, 931 mega electron volts per U, that's what we're going to use in this situation. So that gives me an energy of 937.8 mega electron volts. And we can do this for two other particles as well. So for a neutron, it'd be 939.6. And for an electron, it's 0.511 electron volts, mega electron volts.
So a strange thing happens when we look at the components that make up a nucleus versus the mass of that nucleus when it's assembled. The total mass of the new nucleus is less than the combined mass of its individual particles, which is super weird. And I think that we just need a moment here.
That was from the warm-up.
Right? I know.
So the mass of the nucleus is less than the sum of the masses of its individual particles, meaning that if you take those little particles out of the nucleus and we're able to take the mass of them, individually, they have more mass than when they're combined and stuck together. And the difference in that mass is called the mass defect. And since mass is equivalent to energy, the mass defect is actually the energy released when a nucleus forms. This energy is called the binding energy.
Okay. 1 second. You're saying that if I take a bunch of mass and I pack it all together, it ends up having less mass?
Yeah.
So if I took a 10-pound bowling ball and I put it in a bag, I take another 10-pound bowling ball. That's 20 pounds of bowling balls when they're apart. I take two 10-pound bowling balls and put them together, and I end up with 19 pounds?
That's exactly it.
That's wild. Mass and energy are convertible. So the mass defect equals the binding energy. In the bowling ball example, a 10-pound bowling ball and a 10-pound bowling ball becoming a 19-pound combination, the mass defect would be, well, 1 pound. when that happens with a nucleus, it's a little bit smaller. We are not going to make you solve this one, but it's worth taking a screenshot of. In a helium nucleus, there are 2 protons and 2 neutrons. Let's find the mass defect. You've got the mass of helium, the mass of a proton, and the mass of a free neutron. When we glue together 2 protons and 2 neutrons, something happens. They have less mass. So the mass of 2 protons plus the mass of 2 neutrons is different from the mass of the helium atom. And that difference in mass is called the mass defect. So screenshot that, stare at it a little bit later. The mass defect is 0.030373 U's. If that's the mass defect, then what's the binding energy? There's the mass defect. And we know that 1 U is equivalent to 931 mega electron volts. That means that assembling a helium nucleus from proton, proton, neutron, neutron releases 28 mega electron volts. Now, that's a lot of energy.
It is a lot of energy. The helium has 4 nucleons, and that means that it's about 7 mega electron volts per nucleon. And if the binding energy per nucleon is plotted against the mass number, we get a very interesting pattern that forms. So notice on this graph, the y-axis says average binding energy per nucleon in mega electron volts, and the x-axis shows number of nucleons in the nucleus. And notice how we start almost at 0 with helium-1 and travel all the way up to the greatest point of the peak. Guess what element that is? That's iron. And so if we know that iron has the most binding energy per nucleon, that probably means that iron is the most stable. And inside iron, the nucleons are the most tightly bound. But notice way off on the right-hand side, what elements do you see there? Uranium. And we know that uranium is pretty unstable, especially uranium-238.
Elements lighter than iron undergo fusion. They stick together. Elements heavier than iron undergo fission. And that graph explains how it can happen. Heavy isotopes like U-235, they break apart. They become more tightly bound. Their binding energy per nucleon goes up. Light isotopes stick together and become more tightly bound. My favorite textbook author, one of my favorite physics teachers in the world, Paul Hewitt, draws the graph like this, not as binding energy per nucleon, but as mass per nucleon. We can see that iron has the lowest mass per nucleon. So just like a stretched spring will spontaneously pull itself together, if nuclei can, they will spontaneously emit particles and rays to lower the mass per nucleon. This is another question that we're not going to stick you with just in the interest of time. This came off of an old AP physics exam. You may want to take a screenshot of it. It has to do with deuterium nuclei fusing and forming helium-3 and a neutron. I'll put the answers up on the next slide, so you'll want to screenshot that too. First, we find the mass defect, then we find the energy released. We convert that to MeVs and figure out how many times we have to do this to power a city for a year. Screenshot. Had to take my screenshot pose. So we did it.
Okay, last thing. Einstein left us with one more important idea. And he said that measurements of length and time do depend on your speed. And properties of space and time cannot always be considered absolute. And maybe you've heard this before when we talked about the pair of astronaut twins, and one of them spent time at the International Space Station for X amount of days and came back, and they actually aged a different amount because time was dilated. You're not going to be expected to make any calculations on this, but it's just an idea that there is this thing called time dilation.
The only thing about that you, a smart AP physics student, need to know is that different observers of the same phenomenon, if they're moving at different speeds, taking really, really good measurements, they're going to disagree about length. They're going to disagree about time. But what two people will never, ever, ever, ever disagree on, what is always measured the same for every observer, is the speed of light. That's why it's considered a universal constant. No matter how you are moving or how someone else is moving, when two people are mutually moving relative to each other, they might hear things differently. They might measure length differently. They might measure all kinds of things differently, but they will never measure a different speed of light. It is truly a universal constant.
All right, so just some quick guided practice for you, and we're going to answer 3 questions today for guided practice. The first question is about neutrinos and positrons. The second is about conserved quantities and decay. And the third is about relativity. Here's our first question: carbon-10 decay products. Okay, I'm going to skip past all of this junk up at the top and say, which of the following correctly describes a similarity between the neutrino and the positron? I don't think we talked about neutrinos or positrons at all in this lesson. So I bet you, I'm not going to know if they're positively charged. I don't know if they're massless, and I don't know if they're beta particles. I know what a beta particle is. That's just an electron. So answer choice B is going to give me the right answer for this one, because they're both fundamental particles with no known substructure, pieces that are smaller than a neutrino or a positron.
And I want to highlight something great that Mr. Eaton did there. Folks, I don't know if you noticed that, but he started by reading the question first. Which of the following describes a similarity between the neutrino and the positron? In the reaction above, he said, this is chemistry. I don't chemistry, I physics. So he read the question to tell him what to look for in the information above.
That's exactly it. All right, so we have a second question that's almost identical, but it's asking something different here. Which of the following is conserved during the decay? So looking at the mass number across the top, I can't tell if mass is truly conserved because I have that weird symbol in between, what is that, boron and the electron over there on the right-hand side. Particle number. 651. Okay, total charge. Total charge sounds pretty good. Number of protons. 6.5. The number of protons is not the same. That's for sure. So the answer for this one is going to be total charge. That's something that we touched on earlier, is that the total charge is going to remain conserved in a decay.
Yeah, but in a nuclear reaction, particles lose mass. The end result is always a lower mass than the beginning. The number of particles can change. One nucleus can become several particles. And the number of protons is not necessarily the same after a reaction. In this case, carbon has 6 protons, but then it goes through decay and becomes something else. Now, this is the release of a positron. Obviously, we didn't talk about all kinds of nuclear decay, but in this case, notice the number of protons went down. There were 6, and now there are 5.
Okay, third question. We actually have 4 questions for you today if we have time for it. Observer 1 is at rest. He's stationary and watches observer 2 traveling on this little rectangular shaped spaceship at relativistic speed. That means it's a really big speed. It's a significant fraction of the speed of light. Observer 2 shines a laser at the screen and measures the speed of light, which will be the exact same as measured by observer 1 and observer 2. I remember Mr. Mancino said something about something that they will never disagree on. And I think it's the speed of the laser light through the air in the spaceship, because both of them can see it and they are not going to disagree on those 2 measurements.
All right, last question. What is the mass of an object with this given rest energy? Now, we're not going to make you do it because AP Physics 2 is not a calculator class. Mostly, you can put your calculators down. Mostly. But this is the kind of question that you would see on a test in your high school class or if you took physics at a university. Option A is totally not highlighted. It's not marked with an A, but that's on me. The important thing to know is that 1 electron volt is 1.6 times 10 to the negative 19 joules, and that E equals mc squared. So we know the rest energy, we know the E, we know the speed of light is 3 times 10 to the 8th meters per second. So the only unknown is the mass of 3 kilograms. 3 kilograms is not a lot of mass, but it's a lot of energy if you can use it. Okay, so here's a quick rundown of what we did and what I'm hoping that you walked away with. First off, radioactivity happens radioactivity happens spontaneously. It's governed by statistics. It follows those half-life curves. So I hope that you picked up what half-life was. There are 3 types of radioactive particles, and they interact differently with matter. Alpha particles, beta particles, and gamma particles are differently penetrating. They can be bent differently by magnetic fields, and they have different masses. Mass number is conserved in nuclear reaction, just like charge is conserved in a nuclear reaction. And finally, when nuclei combine or separate, the end result is less total mass.
All right, and can you answer these 3 questions? Which radioactive particle is emitted and when? How do you convert from U, AMU, to electron volts? And how do you calculate the mass defect after a nuclear reaction?
So here it is. Here's your AP exam practice question. I'm going to warn you the font size on this is kind of small in retrospect, so definitely take a screenshot, a good high resolution one. 4 separate hydrogen nuclei together have that given mass, but a helium nucleus has that mass. In the sun's core, the result of a series of nuclear reactions is the conversion of 4 hydrogen nuclei into a helium nucleus. Which of the following best accounts for the difference in mass? And also, so screenshot that. Different question, same vibe. How does the sun's mass change over time? Does it lose mass, gain mass? Does it stay constant? We'll get back to you on that tomorrow. Okay, we know that not everybody has easy internet access and a device to access the internet, but everybody should have the chance to take the AP test that they've worked so hard to do. So if you have any trouble getting online or you need any tools to get you online, reach out now to cb.org/tech and they will get back to you. All right, thank you so much for joining us. Come back tomorrow. Goodbye from me.
Thanks again, everybody. We'll see you tomorrow.